Hello, everyone. Hope everything is going great. Welcome back to the MICCAI seminars, where we welcome Ege. Ege is a third-year PhD student at the Technical University of Munich, where he completed his bachelor degree as well as his master's degree. Ege have been working on his research topic, focusing on holistic operational room domain modeling, aiming to achieve a comprehensive understanding of the operational room using semantic graphs as well as while using large language models. So Ege's outstanding contributions to the field have been recognized either in journals or at conferences, with his last contribution that received the honorable mention for the best paper award in the main conference. Thank you, Ege, a lot for joining us, and thank you for volunteering for giving us this wonderful seminar.
It's my pleasure. Thank you for having me. To share my screen, I think you need to allow me. Yeah, perfect. It's good. Great. Okay. Good. So thank you for the introduction. As you mentioned, my work centers around holistic operating room modeling with large language models, large vision language models. And the goal of my talk today is to really give a bit of a holistic overview of the research directions and focusing, of course, also on the paper you just mentioned called Oracle. But to make sure we are all on the same page, first of all, what is surgical data science? To understand that, we need to understand a bit the flow of surgery so far. It has started as a very rudimentary practice where not really, it looked like butchery essentially on humans. But nowadays it looks a lot different. Doctors already specialize very specifically on certain diseases or cases and really have to consider a lot of different things, use a lot of different devices to treat the patient in the best way possible. And we see that this is going to be increasing in the future, not decreasing. So the complexity is likely to be much higher. However, this is not a bad thing. It sounds like a bad thing, but it's actually a great thing because it leads to higher safety. It leads to better patient outcomes and more illnesses that are becoming treatable. However, the complexity is also increasing and the training requirements are increasing, etc. So this is where surgical data science comes in. Essentially, the goal is to improve the quality of interventional healthcare by capturing different types of data and processing, analyzing them, and modeling certain things. To what end? To create smart systems that can predict events or different clinical outcomes and so on. So the goal can be essentially summarized as, at least for me, when we see a surgery like this, can we understand what's going on a really fundamental level, similar to this head surgeon that's performing the operation right now? To this end, we believe we need to use every input, every modality that's available in the operating room. We need to then develop decision support systems, context-aware intelligence systems that can allow us to automatically adapt to certain functionalities or automate certain steps, etc., of all the systems in the surgery. To give just quickly a bit of an overview of different works that have taken place in this field and how it started and examples of some modalities. One modality is tool data. So we have multiple tools in this surgery that's always increasing, digital tools. We can directly work on this data and it is low dimensional, so it's relatively easy to handle. And it's also easily interpretable. And there were some works on this from Ahmadi et al. That focused on really recording a lot of these different tool signals and looking at them and understanding something about the surgery, such as when certain phases started, or it allowed you to synchronize different surgeries. Oops, sorry. However, this was, of course, limited to tools where you were able to get this information rather quickly. With the advent of deep learning and laparoscopic imaging, laparoscopic video, a lot of interest was turned into just understanding a scene from this laparoscopic perspective. There were a lot of methods. As far as I know, this is one of the first ones that worked on this task of detecting phases, detecting tools, detecting actions on those laparoscopic images using a model they developed called EndoNet. This really opened up a path, and there were a lot of research done on it, such as Techno from Tobias, from our chair actually, who worked on different aspects of temporal modeling, and so on and so forth. And more recently, the task has been a bit more complex, where people are focusing now on recognition of instruments and two-sheet interactions. So you need to detect an instrument, an anatomy, and detect how they interact with each other. This has been a very popular direction as well, and we see this is getting more and more popular. There are other modalities though, so I would say maybe 90–95% of the focus has been on laparoscopy in the last years, but there are other ones such as audio cues, which can be very interesting. I think the audio is sadly not hearable over Zoom, but these events you see right now have distinct audios that a model could use to understand. Similarly here. And we believe that's also a very interesting direction. Coming to the modeling, the patient data aspect, we are mostly treating a disease, but indeed, surgeons are actually looking at the patient to understand what's going, the best course of action to take. So there is imaging of the patient, prior diseases of the patient, age and weight of the patient, and ideally all of this needs to be considered. As an example, in this surgery, in this surgery, a pre-registered CT scan of the patient is used to guide the robot, and ideally we would have access to the patient, we would have access to the CT scan to better understand what's going on. Having said all that, I'm going to mainly focus in this talk on RGBD multi-room information from external views. This has been a field that has really not been focused on a lot, and we have introduced some initial works a few years ago, and that has really been my research direction from that point on. And why is this interesting? Because laparoscopy, assuming it is even a laparoscopic minimally invasive surgery, it would only provide you the view from the inside, but we want to really holistically understand the entire room. And we want to do this using mostly scene graphs so far. So scene graphs are not a new concept. They have been around since early 90s, used by actually Pixar as an example to model a scene in a structured way, and like this, and then animate it semi-automatically into a movie. Now, I have a very short video to show why this is actually interesting for us, because Pixar was able to essentially condense the information from different movies as scene graphs, or in other words, because they had one scene graph describing a certain semantic action, they were able to generate different movies from it. And you see here how it looks very similar semantically, but of course, the texture is different, the lighting is different, and so on. Now, this is actually something that is very similar in the operating room. The surgery in the semantic way can be very similar, but it can look a bit differently. Texture can be different, the colors can be different, the exact positioning can be different, but on a semantic level, these different things will look likely very similar. So we want to work on this level that kind of fuses everything together. And to this end, we have actually now, I think 3 years ago in 2022, published this paper called 4D OR, which won the Best Paper Award at MICCAI, where we proposed the first 4D OR dataset for knee surgery. This was the first real 4D dataset with scene graph annotations that also included annotations for role prediction and face recognition. And it looks like this. So we had 10 simulated total knee replacement surgeries, 3D human pose information and object pose, semantic scene graphs, and clinical roles. It was RGBD, so we also had depth information, and we also had point clouds that look like this. And this is why we call it a 4D, because we have 3D point clouds and then a fourth dimension, which is the time. Then the dataset had scene graph annotations, essentially summarizing all the information in the scene by describing the entities in the scene as well as how they're interacting with each other. And finally, we proposed this method that was a bit, had a few building blocks. It had a 3D human pose prediction block, a 3D object detection block, a scene graph prediction block, and a final role prediction and face prediction block. But essentially, it was able to condense all this point cloud information and the images into a scene graph summarizing what is going on in that scene. We followed this work up with Labrador. I'm going to go mention this very shortly. Essentially, 4DOR was only looking at one single frame or one single time point, but we, of course, surgeries are temporal, so we wanted a method that can, without a lot of overhead, consider what has happened before. And we realize we are arguing that scene graphs are such a good representation of what is going on, so they are also a good representation of what has happened so far by simply integrating what the model has predicted so far for the previous frames into the information we have of the current frame. We get to make a much better prediction. Because the scene graphs are already very highly semantic and have a low dimension, this really didn't introduce a lot of cost into the inference. And the network was able to really see everything that has happened so far. And this not only lead to much more consistent predictions, but also gave us actually an explainability angle. We are now able to see what the model is, which information the model is considering a lot while predicting the current scene graph. Which brings us to Oracle, which won the Best Paper Runner-Up Award last year at MICCAI 2024, where we focused on the task of adaptability and knowledge guidance adaptability in changing OR domains. And we believe that large vision language models are a perfect fit for this. The problem with the existing methods I have proposed so far are that they really fail to adapt to novel concepts, such as seeing a novel equipment for the first time, or even if a tool appears slightly differently in inference time. We really believe that for affordable healthcare around the world, we need a system that's scalable, adaptable, and robust. And we saw some potential in how large vision language models can help us get there. Because we realize the large language models themselves have a really good understanding of high-level surgical concepts. They are good at integrating multiple sources of information, and they can have a flexible output. However, we notice they are really not at all familiar with the exact steps and annotations present in our dataset or any concrete dataset, as well as the large vision language models, so the vision aspect here is really insufficient to understand the operating room. And here we have one example. It looks maybe meaningful at first, but if you really look into it, it doesn't make sense. The scene graphs that were predicted by this large vision language model says something like head surgeon instrument table cutting. This doesn't make any sense. Assistant surgeon instrument table cutting, and generally a lot of things that really don't make any sense. But we still believed in their potential. And so we decided, okay, we cannot just use them. We have to build around them. And we came up with this framework, which we term Oracle, which can take multiple images, as many as you have from the operating room. So we don't have a fixed number anymore. We encode them and use an efficient pooler to pull them into one image representation. And then secondarily, you can have a knowledge branch or a knowledge, I guess branch is the best, or prompt, where you can give additional information, such as the temporal information that tells what has happened so far in the surgery, the textual information, where you can say how a certain tool looks like, or how a certain predicate looks like, or how a certain equipment looks like, and similarly, the visual descriptors, where you can say the same thing by using small cropped images of that action, of that predicate, of that tool. And then we have a fully end-to-end model that takes this information and directly produces a scene graph out of it in form of subject, object, predicate triplets, which we then convert into a scene graph. We needed to take some design choices that, because I mentioned large vision language models don't work that well for operating room. How did we get there? So the first thing that was important was we noticed we need to fine tune on our dataset, and we did it using LoRa, which was an efficient way to fine tune. And just an interesting tidbit here, we even needed to fine tune the image encoder, which is not usually the case. And I believe this is because the operating room modality or domain is just so much different than what is otherwise available online. So the image encoders were really not familiar. How about multi-view input? This was also very, very important for us. Large vision language models, most of them, or almost all of them actually only support one image as an input. And nowadays this changed a bit, but that the solution they usually go with is the next solution, concatenating multiple imaging embeddings. They just add them together, and this has a very high computational cost because attention is quadratic, so you cannot just keep on adding more and more huge representations. This is really, unless you have a lot of GPUs, I guess, but this is not very an efficient way of doing it. What we propose instead is what we call a learnable image pooler, which is a much more smaller two-layer transformer architecture that's trained end-to-end with everything else, whose job it is to take as many image representation as you can give it to it and compress it down into the space of one single image. The next question was how to represent even scene graphs as sequences. So the core idea here was to encode them as a list of triplets, such as head surgeon, patient, suturing. And here another question came up. We can either let LLM natively work on these strings, or we can switch to a symbolic representation with letters and Greek letters. And I will talk about why this was interesting. The initial approach of using an LLM was the simplest approach, where you just encode this list of triplets using the tokenizer of the LLM. And this has the advantage of utilizing the intrinsic knowledge of the LLM. However, this leads to some sort of overfitting, not the traditional sense maybe that you think of, but the model gets used to certain concepts, such as head surgeon never assisting the assistant surgeon. And now the knowledge guidance becomes quite difficult because no matter if you tell it that the saw is green now or red now, it knows it already associated the word saw with the concept green because it was like this in the data set. So we realize it's actually very important to switch to a symbolic representation where for each training sample in the data and for each of them differently, we replace each entity with a random letter and we replace each predicate with a random Greek letter. So a scene graph looks like AB beta. The key idea here is, of course, this now became gibberish. This is not understandable, is to provide a definition table in the prompt itself, explaining what each letter stands for. So such as A is the primary operator in the surgery, handles critical task, or epsilon is a use of a tool, wide, small, straight, etc. The idea here is the model is now forced to attend to these descriptors, and this avoids the overfitting on concept names. And most importantly, you can change and modify these descriptors in inference time and have the model understand those concepts. We also did it similarly with visual prompting. So instead of describing it with wide, small, you can just use actual images here and say, this is how that tool looks like. This is how that entity looks like. And what this allowed us to do is we were able to actually now, unlike previous methods, solve problems such as having this new robot that our model doesn't know, but suddenly it understands, this is the MICCAI robot, which is close to the patient, and this is a scene where head surgeon is robotically solving the patient. Or in the right example, this suture is a very different looking suture than what was available on the dataset. The non-adapted model gets confused and thinks this is head surgeon being close to the patient, whereas it's actually head surgeon suturing the patient. So this method of being able to adapt in inference time really worked well, and we achieved really, really good results. And we believe this is kind of a very interesting way in the future to bring these models to a lot more operating rooms without necessarily needing to fine-tune them for all different kind of cases and different operating rooms. Having said that, I want to provide some future outlook and kind of tease a bit the latest things we have either published or are working on. And this is mainly the kind of the direction of holistic OR domain modeling. And if you have noticed, the last things I talked about were mainly about external room. And I said some people worked on tool data, laparoscopy, and audio. However, to really achieve holistic OR domain modeling, we need to consider all of this together, which would lead to more accurate, more versatile, more robust models, more robust methods. But this requires a high level of integration and manual data collection efforts in the operating room. And we have been working since 2 years on this new data set that is supposed to be much more interesting for the community than for the OR was. It has been in a huge collaboration with different surgeons and companies. And we call it MMOR because it is a multimodal operating room data set where we have 15 full-length surgeries and 30 plus clips with different variations and anomalies of a partial and total knee replacement surgeries with this MICCAI robot. And this is how the different modalities look like. So for one time point, you have 5 images from external cameras with RGBD information, all calibrated, which means you can get a point cloud out of it. Then we have detailed views, detailed RGB views of additional spots in the surgery, such as the instrument table, very close to the knee of the patient, etc. Then we have the screen of the robot, which we are also filming. The screen is used by the operating crew, by the robot technician during the surgery, and by the surgeon to understand a lot of information. And we have a high resolution recording of that. In addition, the operation requires a navigation system. So that navigation system essentially tracks a lot of tools. We also have that information in the data. And finally, the robot has some debugging logs it is producing during the operation. And we have those as well, such as pedal press downs, etc. We have an additional camera, which is recording the surgery in a much lower exposure. So if everything becomes very bright, this camera will still provide some useful information. We have sound from 3 lavalier microphones from the head surgeon, assistant surgeon, and robot technician. And you can use it both to understand the certain frequencies, such as the sawing sound, but you also hear the transcripts, what they are saying to each other. We have, again, scene graphs similar to 4D OR, but in this case, we also have panoptic segmentations from 3 angles, and this makes it also the first panoptic segmentation dataset for operating rooms. And finally, we have the 3 downstream tasks in addition to those, such as the robot phase, next action prediction, and sterility breach detection. I have a very short video, kind of a teaser of this dataset. I hope it kind of gives you an idea of the different camera angles we have, the point cloud that kind of brings everything together. Here we are now going into the robot screen. We have this full high resolution. We see different steps there. We have this low exposure, and this is the tracking data that I was talking about. Here is just a basic visualization of the robot logs, what you see when you're looking inside the robot, certain steps that are completed, etc. And here is the 3D segmentation, 3D panoptic segmentation, and here are the 2D panoptic segmentation. So we have both of them. I say 2D, but it is video, so you can use it for video segmentation task. And this is a chaotic, I must admit, a visualization of the scene graph, meaning all the connections they have. And this is kind of an overall picture, overall overview of the data set. These are some panoptic segmentation results we had. And we wanted to not only publish this data set, we wanted to have a baseline method that now actually is able to utilize all this modality that we are introducing in the data. And we achieve this through a method we call MM2SG, so multimodal scene graph generation method that takes all of this, and some of them are processed through an image encoder, kind of similar to Oracle. Some of them go through a point cloud encoder, or an audio encoder, or a segmentation encoder, so modality-specific encoders. And some of them, such as speech, not the audio, but the speech, so the transcript, some metadata, some tracking data, and the memory scene graphs, are directly processed as text, and all of them are fused in one large language model, which then predicts, very similarly to before, a scene graph summarizing the surgery. And finally, we can take that scene graph and use it to predict sterility breaches, robot phase, and next action. So this is the final visualization of kind of the, let me kind of zoom into the middle, kind of the predictions we are getting. So I'm only visualizing the scene graph here, but the model also doesn't just use these 5 images you see, it uses all the modalities holistically to come up with one prediction. And actually, this is it. So this is where I usually stop. If you have any questions, let me know. I have some backup slides on some potential application of surgical data science. If there are any questions on that, feel free to ask. But otherwise, I would stop here and just ask if you have anything that is unclear, if you want me to talk about something more in detail, etc.
Thank you, Alok. Thank you, Alok, Ege, for this wonderful presentation. It was really inspiring. I really liked, honestly, the way that you dealt with overfitting with the LLMs and how you transfer the concept names to the Greek numerals, as well as the new data set that you're currently providing. I have a question.
Please.
Not familiar, so familiar with this field. So I was wondering, do you need to capture long-range dependencies for the, I would say, the domestic modeling? And how do you do that if you need to?
Let me quickly go. This slide is, I guess, the best to explain. So essentially, I would say yes. I would say you might even need very, very long range dependencies because some actions are looking very, very similar in the images. One example would be cutting and suturing are very similar. You need to really understand that specific tool to differentiate them, but actually it's much easier to differentiate them semantically because one will happen if everything has happened. So one will happen at the end of the surgery and one will happen at the beginning of the surgery, very roughly speaking. So having the ability to understand the long-term dependencies makes these tasks much more easier. And this is exactly what we see in this example. When the model predicts suturing, what it is really doing when you visualize the attention is it is looking certain keyframes and checking if they have happened. It's checking if you had the drilling already, if you had the sawing already, if you had the hammering already. And if those happen, it knows, okay, we are at the end, towards the end of the surgery. So how we are doing is, to come back to that question, is really mainly through memory scene graphs. By actually providing what our model has predicted so far, we are able to tell it, look, 1 hour ago you predicted this, 30 minutes ago you predicted this, 20 minutes ago, etc. It's actually much more denser than what I just described, but that can give it a feeling of understanding certain key moments of the surgery.
Thank you a lot. That's quite interesting. Thank you. Also, there was a question raised by people who were registering for the seminar, which mentioned that your research involves semantic scene graphs and vision language models. How do you ensure they generate trustworthy and clinically relevant explanations? And given that it's clinically relevant explanations, where do you see explainable AI in the next 5 years in this topic?
I'm thinking if I have any good slide on this, I would just keep it here. So essentially, while let me put it this way, the entire idea of modeling everything with scene graph is actually the goal of having an explainable method, right? So we are not trying to have a model that just takes everything as input and provides you one output saying patient is, or even more, like just gives you an advice on do this. Instead, we are proving by having the scene graph prediction that our model is generally understanding what's going on. So we are directly working on a structured representation that is on a high level, summarizing everything that's going on in the surgery. And this is a representation that we kind of came up with together with computer scientists and clinicians to make sure it made surgical sense. And I'm not even claiming that this one representation in the way we defined will solve all the surgeries, but I think it's a very extendable and flexible way to represent the complexity in the surgery. And I feel like the explainable AI research will or should go a bit toward these high-level explainable, kind of inherently explainable representations and not kind of grad camp to see where my model looked at on those kind of things. I think those have some value and some value, especially in understanding the model behavior, but the clinicians don't really care about that. They really care about can I interact with the model and reason together? Can I ask it, why do you think that? Can I see the proof of how it came to that conclusion? Those kind of things. So if this model, as an example, tells you this is the scene graph and therefore I'm saying this is the face, then you can trust it more. And similarly in other medical imaging areas, if you can really see, okay, it's really getting everything and then it's telling me this patient has a pneumonia because of ABC, then you trust it. If it just points out, I looked at this region, that is helpful, but that's not the end all be all of it, right?
Yeah, thank you. I think this answers the question. Is there any questions from the participants? Feel free to just like open your mic and ask the question, or you may drop it on the chat and I could read it for you. So yes, there is a question from Yangli. Thank you, Ege. Do you have downstream tasks after getting the semantic scene graphs? How would you use these graphs in any downstream task, I would say? And how do you know the modalities you use are contributing to your model training?
Okay, that's an excellent question. So we are actually already on the correct slide for a few of those questions. You can do a few things with these scene graphs. So one really, for me, beauty of it is because it is structured, parsable, and explainable, you can just develop rule-based methods or heuristic-based methods that takes a sequence of scene graphs and predicts something. So you can, and this is actually what we have done in the original 4UR paper. We were looking at a series of scene graphs. It was saying human 0, human 1, so we didn't know the roles yet. We understand some human is doing something, but by looking at them and collecting some statistics, we understood, okay, there is one human node that seems to be doing a lot of drilling patient action, and then there is another node that's doing a lot of lying on the operating table. And then by simple heuristics, you can infer one is the patient, one is the head surgeon. Similarly, for other phases, you can detect certain events that happen in the scene graph and associate them with certain phases, just rule-based. But actually, already in the 4UR paper, we were proposing a second approach, which was performing better, but it is a bit, it requires some training data. And this is by using a graph neural network that can take as input those scene graphs that you have predicted and then make a prediction by using them. So it is learning-based method. It understands how to interpret those scene graphs, but it is not looking back at the images or back at the original data, which makes it more robust. If the surgery images itself change, but the scene graphs remain similar, this model's performance will not change drastically. So that's one good aspect. The negative aspect is you need some data. Regarding the multimodality, let me get to that and do it in 2 stages. So first of all, those were 2 downstream tasks. Here in this new data set, we have 3 more downstream tasks. So you have some to choose from. I think these are not even only the ones that you are the only possible options you can do. I think there are a lot of applications of generally being able to understand the surgery beyond these points. So it's not like you're doing scene graph detection just for one of these tasks. Regarding the multimodality, so this is now an accepted CVPR paper that is also on arXiv already available, and we have a huge ablation there showing how the performance improves slightly, but continuously with every different modality you introduce on top of using these 5 images. So this is kind of the basis. You can just use the Azure images, the 5 external views, and we keep adding, and the performance improves and improves and improves. So that was one way to validate it. This doesn't mean, and this is very important, we train this method to be robust to modalities. It doesn't rely on all modalities being there for you to use it, but we show a continuous improvement with every added modality, if that makes sense.
Super. That's a very great answer, and congratulations for the acceptance of the paper.
Thank you.
Nice to know. I have a question, maybe also like adding on the second question that you just answered. So you have performed this during the ablation studies. Is there any way by any chance to know the contribution of each modality during test time, I would say?
I think, yes, we didn't do full study on that, but essentially what you can do is, that's a good, so also during test time, actually, you get to input any modality you have, but you don't need to input it. So the way we train this model is really completely randomly sampled during training how many modalities it sees, so it can take any one of them. And what we have seen, what you can do is really then to take one sample and remove one modality and add that modality and see how the performance change, and not maybe even the performance, but you can look how much the logits change. You can similarly take that embedding and maybe add -100 plus 100, really perturb that embedding and see if the performance is affected by it. I would say the second one, I'm not sure, because we didn't train this model to react to bad representations. We trained it to react to non-existing representation. So I don't know how that would affect. And I think not all of the modalities are clearly used equally, right? I mean, to detect the scene graph, if the robot log says pedal pressed down, that's not as important as actually seeing the scene. But I think everything plays a bit of a role, and yeah.
Super. Thanks a lot for this wonderful discussion. So, is there any questions from the audience? So, if not, we would like to thank Ege. Thank you a lot for joining us today. It
Thank you
was,
for having me.
and